Hi, in this episode we'll conquer a very interesting new algorithm called the Egyptian Skyline problem. So it's very similar to the leak code, basic like Skyline problem, but except this one has a little more difficulty. It's going to be basically in the recursive steps of divide, conquer, and combine and merge. We also have the array M, which will be able to rotate between the triangles of the problem, and also it's very similar to a Bloch curve. The Egyptian Skyline problem is a very simple recursive algorithm. And also it's a very efficient algorithm, O and log n. Let's get down to business. This should be second nature, but of course subscribe to the channel, and this is for the channel of Jason Liu. As you can see, I made some pretty nice Giza pyramids. Before the pandemic, I really wanted to go to Egypt after Northeastern graduation just to really enjoy algorithm in terms of architecture, but I guess that's going to be held off for now. So let's get down to business with the Egyptian Skyline problem. So the problem is defined as follows. You're basically, let's say you are, Indiana Jones from the Kingdom of the Lost Skull. You're trying to find some sort of way to check all the pyramids to find, some lost jewelry from the Egyptian pharaohs. Pharaoh wants you to basically infiltrate the pyramid. So let's say from a far distance, you see the pyramids looking like somewhere like this. Like a bunch of spiky things, right? And you're wondering, how do I actually know the skyline of a pyramid? Which is defined as basically the length of the outline from the illusion. And the tricky part in this problem is unlike that of the good old regular, the good old regular rectangular skyline. That's a very crappy version drawn in Boston, unfortunately. But besides that, it's also very challenging to understand where exactly does the skyline start. Ordinarily, geometrically, we start from the point 0, 0 for a skyline in the skyline problem. In this case, we also start from point 0, 0, but we have to be careful where we start inflecting or changing the points. So to help us geometrically, you should remember your good old trigonometry, right? SOHCAHTOA, which is sine, cosine, and tangent. We're going to use trigonometry because one of the key principles to the Egyptian sky problem is that each of these little things is technically an interposed pyramid with points A, B, and C, and that you rotate with the skyline with the following array. M equals root 2 over 2, 0, 0, and negative root 2 over 2, which in very simple layman terms means you basically rotate by 45 degrees, or perpendicular, but first you rotate by 45 degrees every time you draw a new skyline. So this thing is basically very similar to that of drawing like a cool Bloch curve, which I will show later in the comments what a Bloch curve is. It's basically fractal. So we're trying to use recursion and divide and conquer to find the skyline fractal for the Egyptian skyline. So yes, this is called the Egyptian, not the regular leak code skyline problem, the Egyptian skyline problem. I want to go to Cairo to actually see the awesome skylines. So I'm going to show you next how to solve this problem using divide and conquer and good old recursion. Just like that of the first ever episode from the Jack Sparrow, dun, 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 like the Jack Sparrow finding the heart and the bottle of rum. We use the divide and conquer principle. A quick refresher. Divide and conquer is you have this problem, you divide into a bunch of sub-problems, then you merge and combine. So that's your divide and conquer paradigm right there. Very, very simple, very straightforward. It's like breaking a piece of chocolate and eat it piece by piece, or sub-problem by sub-problem. Also, fun fact, later in the problem sets, we're also going to use divide and conquer for other data structures, such as hash tables. That is for another topic. So for this one, we use first the divide step for divide and conquer. And this one is a little unusual. So we essentially partition. That word is going to be very key in any interview problem you have, is to use the word partition, which means break into separate equal segments. Partition the, let's say, n total pyramids in the outline into a set of 2, which means you have, similar to that binary search, a high subset and a low subset. So essentially we're trying to charge our real smooth now. Instead of between 2 points, we try to have real smoothing between essentially 3 points on each pyramid. This is a much more advanced version than the Jack Sparrow one. So you can see, computer science likes to build upon itself in each different problem set. That's why interviews get tough. They give you an easy version, and then eventually it gets you to the lead code hard spend all day long to solve a one problem version. So formally, we define each particular point of the pyramid in terms of a tuple A, B, and C, which obviously from a triangle perspective, point A, point B, and point C. That's not too bad. Then the conquer step, we have it pretty interesting. We have 2 pointers to basically determine the high and low. We're trying to merge them together in terms of like a recursive merge sort type of thing. So you have basically this thingy as the low partition, and then plus this thingy, which is the high partition for the pyramids. So for the conquer step, it's pretty interesting. For the conquer step, we set 2 to continue onwards. So we have 2 points I1 and I2, and then we have to make them equal to S1, comma S2, which is the skylines of the pyramids. Then we could do a little bit of linear algebra. We do a little bit of like in terms of tuple work. So if S of I1 equals to 2 coordinate points x1, y1, and then S of I2 equals to coordinate points of x2, y2. So in layman terms, it's basically saying like every time we have a point of a skyline, for example, if we magnify this, this is going to be x1, y1, and every time we have a point skyline, that would be a piece, s1. So that's how you like show we have like a different form of a skyline. It's when we magnified this in terms of the skyline. So next, we build the skyline recursively. So recursive on this function, draw Egypt skyline. And for the first time, I'm going to use pseudocode in this Algos in 10. So our draw Egypt skyline takes 2 parameters. It basically takes the value of each x to n, and also takes the points A, B, and C in the recursion. So I'm going to show you now how the recursion works in the conquer step. This is a bit of a longer conquer step because it's a bit of a tougher problem. Hold on for me. So we have the conquer part 2 for the recursion, which means we basically have to make recursive calls. So we have the function draw Egypt skyline, or draw skyline Egypt. Oh, I can't spell, I am sorry. Let's draw skyline Egypt. Draw skyline Egypt, which takes the 2 parameters, all the x1 to xn, and also the points A, B, and C. So in a recursion pseudocode, we generally want to do is calculate a midpoint. So we calculate the midpoint to be pretty much equal to the y value of each b. So we have b1 to b of y. Because it's drawn in a nice triangle again. A, B, and C. A, B is on top. A, B, and C. A, B, C. The y value of b is often the highest point in any triangle. That is a property in geometry. So we choose b of y to be the maximum of the midpoints. And then we basically repeat this. So we basically call draw skyline Egypt recursively for up to n pyramids. So we do from x1 to xn again, but this time we do it for A, B, C, and n, which is another parameter. Originally, we just had 0. We had 1 to start off with, but we're going to do draw Egypt skyline up to all the n pyramids. And then finally, we're going to now finish off the conquer step with the following. I'm taking my solution. So finally, we're going to have something called the distance formula, which I hope people understand from geometry what it is. So distance of any 2 points, let's say for example AB, is the following. you have ax minus bx squared plus ay minus by squared. And this, of course, should be in a magnitude because you want the distance to be greater than or equal to 0. If it's negative, you're living in bizarro world. You don't know what a distance is. So let me finally wrap up this algorithm with the combine merge and then the runtime. It's a very fast algorithm, but takes a little bit of thinking to do. In addition, we also make sure we don't forget to call the M array on each of the pyramids as well. Wrap the algorithm with combine and merge. So we have the two distance formulas. We have dist AB and then we have dist BC for each of the pyramid skylines. We're only calculating the points A, B, and C. And do not worry, we have considered the overlap case, which means if you have overlapping triangles, it's not a big deal. You just simply find the difference between the AC and A and C points. We're generally assuming there's no big overlap. So for each of the distance formulas, let's just say this is big A, this is big B. So big A equals just square root of ax minus bx squared plus ay minus by squared. And then big B equals the same thing, essentially with the points B and C. Bx minus by squared plus, bx minus cx squared. And then by minus cy, there we go, cy squared. There we go, that's how geometry works. Thank you, Worcester Academy Geometry. And then we finally finish the algorithm by saying we complete the algorithm by adding up all distances. So basically summing up A and summing up B. And then we would then represent that as a skyline, as the Egyptian skyline for the problem. So Egyptian skyline is interesting. The normal skyline problem, you don't have to use the distance formula. But since you're calculating points between non-horizontal verticals, you're going to have this distance formula. So let me just wrap up this video with the runtime and let me show you what's going to happen next. By the way, comments and also likes if you love Nintendo Legend of Zelda, because that will be what's the next video. A very interesting form of circular recursion with Armos Knights. Spoiler alert. So we finally go for the runtime of the algorithm, which is always important. Do not forget runtime in any interview or you're going to get penalized. So I say out of the blue it's n log n. It's the same as merge sort. Why is it O n log n? Well, it's O of 1 each time we basically calculate the distance between points A, B, and C, because that is just a simple operation of arithmetic. It's again O of 1 when we rotate, because it's once again just the concept of trig arithmetic, trigonometry arithmetic. And then finally, it's O of log n, because we basically do a split, like a binary search, but in this case it's more like a binary split between the high and low partitions. And then finally it's O of n because we're doing for n pyramids. So this is why the ending runtime of this entire algorithm is O n log of n. And there we go, that is the general solution for the Egyptian skyline problem. So make sure to subscribe to Algos in Time with Jason Liu, episode 3, Egyptian skyline problem. Thank you very much guys and have a nice rest of the week.